But in order to design effective management strategies, you need to figure out how what you are doing at the scale of a single farm relates to what's happening at the Gulf of Mexico. Now that's the part that gets really, really tough. The reason it gets tough is because you need to figure out what is happening across scales. So here I said, from the scale of a tile, a single tile drain, to the scale of the tide or the Mississippi Basin, you need to go across scales. So it is easy to figure out, and a lot of people have done work on what is happening at the scale of like a small soil block, all the processes that are happening. But each soil block is different. So how do you know what are the properties in each soil block? Then how do you know what is the property across the catchment? So that is the question that is really challenging. Now, the way this is done, the kind of approach that's normally taken to do this is that this is a watershed. And normally what we do is we sit at the watershed outlet and we measure hydrographs and chemographs. So what that is we measure water quality with time, and we measure the flow that is going past this one point with time, right? And then we divide this area into these small units, right? This is one unit. And in this unit, all these complex processes have to be described. Now think about the watershed made up of a zillion of these units. And in each unit, you need to know what the rates of each of these processes are, what the masses are in the system. So it becomes often an unsolvable problem. The way you get past it is that you kind of put some parameters in this box, and then you say this box is similar to a couple more other boxes. So you have a model with about 20 or 30 parameters. And then you go in and tune those parameters so that you get this output. Now you can immediately guess that if you are tuning 30 things to get one number, you can tune it any different ways, and you would get the same number. So that in our world is called the concept of equifinality or non-uniqueness, non-unique parameters. And then when you use those parameters to say what will happen when farmer A, who lives here, does something at the watershed outlet, you're not really very accurate. And it has been observed, so since the hypoxic zone problem became a huge deal, there's a number of things going on like conservation reserve programs, so a number of activities going on. The main challenge being, a lot of times you see land use change happening, but when do we see the benefit of the land use change? Don't really know, because there is a time lag and it's difficult to quantify. So this challenge, so we propose it. So this is now I'm moving into more my area of research. What I'm interested in is building a different group of models, different kind of models. And this is called kind of the pattern-based model. So there's a group of us who are interested in this kind of a model. So what is this? So the idea is this. We know that we know the physics of what's happening at the scale of a single soil block. But we also know that it's very difficult to go up the scale. So this is called a bottom-up approach. So you start at the small scale and you build your way up. The other way is you start at the large scale and then you kind of narrow your way down. So that's called the top-down approach. And what we say is you need to be doing both. You need to understand the mechanics of the scale, but then you need to be looking at the larger picture and say what is important. So I'll give you the examples in a bit. So the pattern-based approach is based on the 4 P's. The first P is, of course, patterns. So we look across landscapes and we search for patterns in the landscape. And then we say, well, what are the processes that contribute to that pattern? Say, for example, flow through the tile drain may be a process. We know that there are zillion processes going on in nature, but maybe one of them is the main cause of the pattern that we see. So we kind of work our way backwards to say, what is the process that's causing this pattern? And then once we kind of have an idea of the process, we say, well, now we have this entire domain of models that describe all the processes in detail. Which of the processes can we take away? Because it may be not that important. So then we go into the prediction mode. And all of this is tied together by the idea of purpose. We need to, whenever we are building a model, it's necessary that we keep in mind the purpose of the model. As an example, if you're thinking about hypoxia in the Gulf of Mexico, you need to only know maybe monthly loads of nitrogen. That's enough to predict what kind of hypoxic processes would happen. However, if you're thinking of predicting something like a chronic or an acute toxicity to fish, so some discharge of some chemical that causes an acute toxicity, you would need to know a daily concentration or even an hourly concentration. So the model that you would need for both these problems, conventionally it's the same model is used with just different parameters. What we are saying is that you need to be thinking maybe of different models. When you're talking about Gulf of Mexico, you're integrating over this large million square kilometer Mississippi basin, right? So in that case scale, when you're talking about time, you can maybe do a month and be okay. When you're talking about what's happening in the stream over here, you need to maybe be thinking about a different kind of time scale. So depending upon what your interest is, you build your model. So patterns, we start our journey with patterns. Patterns offer a window into landscape processes and they help us build hypotheses. We start out by asking what are the emergent patterns in a landscape. When I say emergent patterns, what I'm talking of is a pattern that's not immediately obvious when you are looking at the small scale processes, but at the large scale you see it emerging. Like a river network, that's an emergent pattern. It has similarity to a tree network, a tree branching. So those are, nature has some amazing things and we learn from it. And then we use that knowledge to create models. So let me give you an example of one of these cases. This is what we did. So when you have rain falling over your watershed, so this is my cartoon watershed and I have the rain falling over that watershed. And I'm interested in understanding what is the stream flow. So I want to convert my rainfall and want to predict stream flow. Now in a conventional model to do that, this is tough because when the rain falls on the surface, it can go through different ways. It can go on top, it can leach down, it can flow through the subsurface. There can be different times taken to travel depending upon the particular geology. And so it's very difficult to go from here, the rainfall, to predict what the stream flow is. But now think about the Midwestern catchments. Think back to when the first settlers came in. You had these landscapes made of wetlands, right? And what they wanted to do was use this for farming. So they wanted to drain these wetlands. The way they did it is that they placed these tile drains, which are these pipes, about a meter or so below the ground surface. So what happens is that when you have rainfall, it goes to these tile drains, and then there's a lot of tile drains all over your watershed, so it flows fast through the tile drains into your stream. So your land remains dry and can be used for agriculture. So basically they created a man-made artificial network that bypasses the complexity, the fascinating complexity of the landscape. So in terms of nitrogen loads, it makes the problem severe because you're not giving it time to react in the landscape. In terms of a modeler's view, it makes the problem simpler. You don't need to consider all this complexity. It's simple. It flows and it flows through the tile network. It's easier to model it because it's just a pipe network. So thus our hypothesis was that human modification of this particular watershed is actually making it simpler to model. And because of our mindset of always wanted to build a complex model, we've not used it adequately, this attribute of this watershed. So this is an example of that. This is work that Keith Schilling at DNR did. So this is one of his papers. I should have had the reference here, but anyway. So what they showed, without going into a lot of details, is that they examined tile drain watersheds and non-tiled watersheds, and found that indeed tiled watershed have a simpler, fast way in which the flow recedes. So there is a very simple signature of tile drain watersheds that you can figure out. So now I won't go into the details of the model that we used using this particular attribute of the watershed. What I'll just say is that we were able to build a model that was able to predict stream flow at the outlet of a 700 kilometer square watershed, as well as the conventional models. While the conventional models needed softwares, ours was done on an Excel spreadsheet. So this is work that just got accepted. So then we said, well, this is stream flow. Can we go from here to say, well, what would nitrogen loads be? Can we link stream flow to nitrogen loads? Once again, we follow our pattern process pathway. So we look for patterns. In this case, we looked for patterns across large watersheds in the Mississippi Basin. So these are large meaning 200,000 to 800,000 square kilometers. And we said, what is the nitrogen load that is contributed by these watersheds? So here we plotted, so on the y-axis in these figures, you see nitrogen load. So this is mass of nitrogen that is discharged by that watershed per unit area, per unit time. And on the x-axis, what you see is the mean annual stream flow. So each of these different colors represents one watershed that you saw in the last page. And each data point is a particular year.